Okay, so here is the Chapter 5 test from Calculus, a First Course textbook. This is on page 247, and I'm going to try and make this test look as easy as possible. So the first one is just finding the limit. So we have our function, we're dividing. If we want to find as x tends towards infinity, we want to take every term within and divide it by x to the highest exponent. So I'm going to take 6x cubed divided by x cubed, because that's my highest exponent, minus 3x divided by x cubed, plus 1 divided by x cubed. And then the denominator, I have 2x cubed divided by x cubed, plus x squared divided by x cubed, minus 5 divided by x cubed. Now, the nice part is the x cubes will cancel with those other terms. And now, even if we reduced our x's, if you plug in the limit, as our denominator tends towards infinity, the whole fraction tends towards 0. So all these other terms will cancel out, and we're going to be simplifying all the way down to 6 over 2, which will just equal 3. So the limit as x towards infinity of our first function is just 3. Now in the second one, it's a little bit more work. We're looking as our limit goes towards a number. So we have x minus 1 over x squared minus 4. But we want to recognize that that is a difference of squares. So we'll split that up or factor it into x minus 2 to x plus 2. Now, if we did plug in our limit, in the numerator, if you plug in negative 2, even if we're approaching from the right, the numerator will still be negative. Then if we take a look at the denominator, if you plug in negative 2 into our first factor, it will be negative. And then if we plug in a value as we approach negative 2 from the right, so something just a little bit bigger than negative 2, this whole factor will be a very small positive. But that means that when we look at our signs, our negatives cancel and we have a positive value. So this means we're going to tend towards positive infinity because we know at negative 2 exactly, our value doesn't exist. So we'll have that asymptote. Now the next part is leading you into asymptotes. So we have our function y equals 1 minus 2x over 3x plus 5. So if we're looking for a vertical asymptote, that I think is always a little bit easier because that just means what x can't equal from the original function. So when we look at the denominator, 3x plus 5, and you isolate x cannot equal negative 5 over 3. That means we have a vertical asymptote at negative 5 over 3. So what we want to do is figure out what's happening at that value. So we're going to look at the limit as x approaches negative 5 over 3 from the left, and we'll also look at the limit as x approaches negative 5 over 3 from the right. So with that first bit, I'm just going to plug in the value into the numerator. We have 1 minus 2 times negative 5 over 3. And in the denominator, you have 3 times negative 5 over 3, but we're coming in from the left. So it would be a value a little bit more negative, and then you're adding 5. So a little bit more negative and add 5. So when we look at what's happening, we'll have a positive, if you simplify the numerator, divided by a negative. So we'd be tending towards negative infinity. We're going to do the same thing with the approaching from the right. So you'd plug it in and same idea, it would be the same answer on the top, but your denominator, instead of going a little negative, you're going to be a bit bigger there. So we'd have a little bit more positive at that point. So we have a positive number plus a positive. So this one is approaching positive infinity. So that's our first part, looking at the limit, what x cannot equal, and what happens when you approach that value from each side. Now the other part we want to look at is a horizontal asymptote. So when you're looking at your horizontal asymptote, you want to know what your limit will be as x approaches infinity and also negative infinity. It's usually kind of the same idea, but just both of those are what we'll take a look at. So if you take a look at your function, it's similar to what we did with that first question. You want to divide every term by your highest exponent. So that's just going to be our x value. So you're going to have 1 over x minus 2 over x divided by 3x over x plus 5 over x. So if we plug in either limit, the last two terms are going to tend towards 0. The first term, will also tend towards 0 here. What am I looking at there? Oh yeah, what am I missing? Oh, this was an x. Oopsie, there we go. Sorry, let me just correct that one so that's a little bit more clear. I only had written down 2, not 2x. So if you divide by x, the x's cancel. So this one trends towards 0. Now this cancels as well, and you're going to be left with -2 in the numerator and 3 in the denominator. So that means that you'll have a horizontal asymptote when y equals -2. Now, putting that together and adding in some information about concavity, here we're looking at our function and we want to know when we concave up and concave down. If we're looking at that, you are looking at your second derivative. So the reason this question gets a little bit more complicated is more the math involved, not the concept. So we need not just the first derivative, but the second. Now, I tend to like to write the product rule, not the quotient rule. So I'm just going to rewrite this with my denominator, bring it up, and just by making that exponent negative. Now instead of the quotient rule, I can use the product rule. So I'm going to first start by taking the first derivative. And when I do that, I take my first term, multiply by the derivative of the second term. Now just using the power rule, we need to subtract 1. And then also the chain rule, but the chain rule, it's just 1 on the inside, so we don't need to write that. Then I take the second term and multiply it by the derivative of the first term. Now I want to factor out an x plus 1, and you always take out your smallest exponent. And when I do that, I'm left with -2x plus x plus 1. And now this simplifies a little bit further, and I'll have x plus 1 to the power of -3 times 1 minus x. So that's my first derivative. Now I'm going to use the product rule one more time to solve for my second derivative. So I'm going to take my first term, so 1, that's my second term, but that's okay, 1 minus x, and multiply it by the derivative of my first term. So -3 times x plus 1, subtract an exponent, and then use your chain rule, which is still just 1 on the inside. Add on, so I did that derivative of the second. So I have to add on my first term, -3, times the derivative of the second term, which is just -1. And just like that math in the first bit, we're going to take out your lowest exponent with that common term, not this one, sorry, of x plus 1. So I'm going to take out x plus 1 to the power of -4. And when I do that, I'm left with -3 times 1 minus x plus -1 times x plus 1. So I need to simplify everything within here, and it ends up being -4 plus 2x all over x plus 1 to the power of 4. So now that I have that, I can solve for x, and I'll see that I have my 1 from the denominator gives my 1 point of discontinuity to be -1, and then from the numerator, what makes the whole thing 0 is going to be the value of 2. So if I do my number line with -1 and 2, at those points, I'm going to possibly have a point of inflection, but I have to do the number line to find out. So I have my factor of -4 plus 2x in the numerator, and then I have the factor of x plus 1 to the power of 4, and then I'm going to take a look at what's happening. So in the numerator, it is going to be negative less than 1 between 1 and -1 and 2, and then once we pass 2, our concavity will be positive, or our factor would be positive. Now in the denominator, it doesn't matter what we plug in, because once we raise it to the power of 4, it is always going to be positive. So then when we take a look at our concavity, the first what pit is going to concave down. Between -1 and 2, it's going to concave down. So -1 is not a point of inflection. And then once you pass 2, it will concave up. So the point 2 is a point of inflection. So when you're writing out with your notation, concaving down, -infinity to +2, concaving up would be 2 to infinity. And your point of inflection, which I guess it didn't ask for here, but we can add it on, is 2. And then you plug 2 back into your original function, and you'll see that your y value will be 2/9. So that's our point. Looking at question number 4, we're putting more together once again. So we're finding intervals of increasing and decreasing. Sorry, my son is coming to ask me a question. Yes, quickly. Nothing?
Can we come inside for the last 30
Yes.
minutes? Huh?
Yes. So,
We're gonna play games.
okay, sorry about that. Just looking at my value of, not my value, my function, y equals 2 minus 12x plus 9x squared minus 2x cubed. If I want my intervals of increase and decrease, that's talking about the slope. So I'm looking at my first derivative. Local max and mins, I still need my first derivative. Intervals of concavity, you need your second derivative, which will also give you that the point of inflection, and then we can graph it. So there's quite a little bit of work here, but it's not hard work. So let's start with finding that first derivative. So if I take my first derivative, I would get -12 plus 18x minus 6x squared. So nice and easy, it's just all the power rule. And then I want to factor, so I can take out a -6 from each term. And when I do that, I'm just going to rearrange it so my x squared term is first. Then I have x squared minus 3x plus 2. And then I can factor the inside further into 2 binomials, and that will be x minus 2 and x minus 1. So that gives me some critical numbers. My critical numbers are happening at +2 and +1. So my first bit, I want to figure out when I'm increasing and decreasing, and that will help me with my graph. So I'll have the value of 1, and then 2, and then higher. So, and then my factors. So I want to include the -6 because that does affect my sign. And then I have x minus 2, x plus 2, and then I'm looking at my slope. So -6 will always be negative at my critical numbers. My slope is 0. For x minus 2, anything less than 2 will be negative. Once we pass 2, it will be positive. And, oh, I have, why did I write that down? This should be x minus 1. So you're probably wondering why I did that. X minus 1. So we'll have negative. Once we pass 1, it will be positive. So for your slope, you are negative below 1. You are positive between 1 and 2. And then you're negative above 2. So if I'm looking at my intervals of increase, I could say that, or I could just write that out. So my intervals of increase would be from, so I'm increasing between 1 and 2. That's an ugly 2, but you get it. And then I'm decreasing from -infinity to 1, and then I use that union. I'm also decreasing from 2 to -infinity. So that's my first part. I also going to talk about my local minimum and my local max. So I have a local minimum at +1. So I can say my minimum is going to be at 1. So when my whole function is 1, I go back to my original one and plug that value in. I'll see that my y value would be -3. In terms of my max, I have, when we're changing from negative to positive, that's happening when my x value is 2. And if I plug it in to my original function, my y value will be -2. So I'm doing all that, and I'm going to use this to graph it in a moment, but I also want to look at my concavity. So to look at your concavity, you need the second derivative. So I'm taking that second derivative and just using the power rule. It's easier to start before you factor it. So when I do that, my derivative of -12 is just 0, then positive 18x is just 18, and then I would have -12x. Factor out your biggest common factor, which is 6, and you have 3 minus 2x. Now this tells me I have a possible point of inflection at, sorry, that's a P, point of inflection. When I set this equal to 0, it's possibly at 3/2. So now I want to test that by doing another number line with 3/2 and my factors. 6 will always be positive. Then I look at 3 minus 2x. Anything less than 3/2 will be positive. Greater than 3/2 will be negative. And because you're switching from concaving up, which is that first part, to concaving down, I'm not sure what happened there, you will see that this is in fact a point of inflection. So that is true. And so that's also part D. So now we have this and this. And lastly, to graph it. So I'm not going to do a really, really great graph, but hopefully you'll get the idea here. And actually I might move that up just a wee bit just to show it. So I'm still using that information that we've already taken a look at. But again, if I wanted to graph this, a lot more is happening in the denominator, in that fourth quadrant there. So I know that I have a few important points, and one would be my minimum and my maximum. So my minimum is when x is 1 and y is -3. So if it's a minimum, we know that we're hitting it and going back up. Then I also know I have a maximum at the point of 2 and -2, which is right here, and then it changes direction. Now in terms of concavity, 3/2, this point here, would just be 1.5. And if I find the y value at that point, it's -5/2. So right in here, I'm going from concaving up, which I'm trying to show here, to concaving down. And then from there, I just want to extend it to go towards infinity in each direction. So that's my very simple graph. The part in here is probably most important, where we're actually showing the intervals of increase, decrease, and concavity. Now, the very last question that's on your chapter test is this one here. And now with this one, it did take me quite a bit of time, and it's not because it's hard per se, like the information here is not bad. It's just, oh, I didn't even write out all the questions, but I'll tell you what it's asking as we go. It's because the math involved gets kind of challenging. So it is a question with a bunch of parts. The first part is asking for domain. So domain here is hopefully nice and easy. Looking at the denominator, x just cannot equal positive or -3. Other than that, x can be anything. The other part asked for intercepts. So if we found our intercepts, we can find it by setting x equal to 0 and then setting y equal to 0, and you'll find that your intercept is at the origin, so it's 0, 0. It does also ask you for the axis of symmetry, and the axis of symmetry in this case will come from the intercept, and that happens at x equals 0. And then the next part is D, asking for vertical asymptotes and your, I believe, horizontal asymptotes. So let's take a look at that. And so that reminder, your vertical asymptote happens, and we look at the denominator for that. So what x cannot equal. So x cannot equal positive and -3. So we're going to look at the limit as x tends towards positive 3 from the left and the right, and then you'll look at the limit as x towards -3 from the left and the right. So if we start with positive 3 and we go from the left, you get a positive value in the numerator, a positive in the denominator, and then a very small negative. So that's -infinity. Then if you come in from the right hand side, you would get positive over a positive and a positive, which is positive infinity. Now the other way I'm doing it, just to make sure we're all on the same page here, is I did factor the bottom because it is a difference of squares when I'm actually looking at my 3 values that matter for my signs. Now same idea, I'm going to do that again from the left with -3. So I have a negative number in the numerator, and then I'll have a negative factor and then a small negative, so that will tend towards -infinity. And then I'll do the same thing coming in from the right hand side, and you would have a negative over a small positive and a negative, which will tend towards positive infinity. Okay, so we have all of that information there. And then it starts to ask you about the intervals where you're increasing and decreasing. So when I'm looking at intervals of increasing and decreasing, you do need your second derivative. But to get there, oh, sorry, no, you don't. You just need your first derivative. But to get there, it is like I mentioned before, I'd rather work with the product rule than quotient rule. I just always think that's easier. So I'll rewrite my original function to be x times x squared minus 9 to the negative 1. So then if I want to do my first derivative, I would take my first term, multiply it by the derivative of my second term, and use the chain rule here. So we'll have a 2x. And then I'll add on my second term and multiply it by the derivative of my first term. Then take out your greatest common factor, which is your smallest exponent for that common factor, which is negative 2. And when you do that, you'll have negative 2x squared plus x squared minus 9. Now, collecting some like terms here, you end up with negative 1, once we factor out, times x squared plus 9. So I'm just skipping a step there, but that's just simplifying this and taking out a negative 1. And then in the denominator, because I do need to look at each factor, you will have x plus 3 times x minus 3, and all of this is squared. So going to look at a number line, and your factors that matter here are going to be negative 3 and positive 3. I wonder why that keeps happening where all that disappears. It doesn't matter though, because we don't need it anymore. So our values that will affect our signs is the negative 1 factor from the top. No matter what we plug into this factor, it will always be positive. And same thing with this part down here. Your denominator, even if we expand it out, which I'm just going to write it as its condensed form, is always going to be positive because of that squared term. So at these values, your slope will be 0. And then looking at what's happening here, we can just fill in what's happening the rest of the time. So this is telling us that your slope is always going to be negative, except at negative 3 and positive 3. It's also asked in this if you have any maximum or minimum. We don't, because you don't have a change in direction for your slope. Now, the very last thing this question asks, if you have your textbook and have been following along, actually it's not the very last thing, it's the second last thing, is to find the intervals of concavity. So that is taking the second derivative, and if you go back to what we just had at the end there, you have negative x squared, so this is our first derivative, sorry, minus 9, and then same thing, I'm just going to rewrite this so that I can use the product rule, because I love the product rule. The quotient rule just gets really messy, but so can this. And I want to take my second derivative using the product rule. So I'm going to start with my first term, multiply it by the derivative of my second term, and then use the chain rule to get that inside, plus the second term, multiply it by the derivative of your first term. Then I can factor out a common term, and I actually end up having another common term of 2x. So I'm going to take out that x squared minus 9, which is going to be the lowest one, is negative 3. And I'm also going to take out a 2x. When I do that, and I simplify as I go, I'm left with 2x squared plus 18 plus negative x squared plus 9. Then I simplify again what I can. That 2x I can't do anything with, so that's still in the numerator. All of this simplifies to x squared plus 27. And the denominator, I'm just going to put that back down, is x squared minus 9 to the power of 3. So lots of work here to get to that second derivative. And again, the math gets confusing, but this is what we have to do. So if you have to pause it, take a second to process that. I'm just erasing this for more space. Now what I want to do is use my number line and recognize I have a factor of -3 from the denominator difference of squares. I have 0 from the numerator. I have +3, and then it goes to infinity. My factors are going to be 2x. I have the other factor, x squared plus 27. And then I have the denominator, x minus 3 and x plus 3. Because of the odd exponent, we'll have to split it up because it will depend on our sign, depending if we're positive or negative. Then I want to look at our concavity. 2x is always going to be negative till you pass 0. Our next one, because of that squared, will always be positive. X minus 3 is going to be negative until you pass 3, right? So just think if you put a negative number in here and then square it -3 and cube it, that's what's going to happen there. And then x plus 3 is negative till we pass -3. So we have concave down, concave up, concave down, and then concave up. So we do have 3 points of inflection because we are switching 3 times between those. So we did all of this work, and then again, I'm just going to have to erase it. When we do put it all together, we have discovered that I wonder if you can hear my dog in the back. He wants some attention. We have discovered that at +3 and -3, you have some asymptotes. Jeez. We also found out that we do flatten out and we never cross 0. The first part, we are going to cross through the origin. Oh my goodness. Johnny! That didn't want to work there. Well, now my whole graph has stopped working, so that's fun. So we are graphing it. We do want to pass through the origin. We do have a messy looking graph here. And I'm really sorry about my dog barking in the background, but I hope this was enough to get you to this point. I'm not sure why my pen's not working anymore, so that's a bit frustrating. Let me try one more. No. Okay. If you did make it this far, I hope this was helpful, and thank you very much for watching. I'm very sorry about that graph. If you did make it and you would like a picture of the graph, I can add one. And if you are in chemistry, please check out my channel and my website. And if you any other video I can ever do, just leave me a comment. Again, thank you for watching.